Good morning, good morning. Welcome back. Happy Wednesday. Today we start on page 25 in the packet, so can we go there? And while we're opening to page 25, just a couple of non-calculus announcements. First of all, Student Senate elections are happening today, yesterday, and Monday. Today's the last day to vote for GCC Student Senator. The way to vote is to go into Moodle, and hopefully, has anybody done this already? Okay, so if you go into Moodle, hopefully there will be some obvious place you can go that says here's where you go to vote for student senator. Each of the candidates has a little statement about their platform, so you can read and get to know the candidates and then pick the one that you feel is most suited for you, okay? But today is the last day in which you can do that. I think it goes until midnight tonight. So log into Moodle at some point today and go vote for student senator. Speaking of voting, we are in the middle of a very important national election, and so GCC has had several events to try to get the student body here more engaged in this voting process. And one of those events is today. The representative from the 2nd Berkshire District, Paul Mark, is coming onto campus today at noon. So right after physics, if you are free and interested, he will have a discussion about why voting matters. And so it's going to be, from what I can read here, it's going to be fairly informal. You can go with questions or you can just go to listen, and there's free food, which is always a perk. So check that out today if you are available. Again, that's at noon, and that's in C208. There is food. It says refreshments. So it doesn't say, like, I think that there's a subtle difference between food and refreshments. And food, I think, is the heartier, you know, kind of like pizza maybe. But anyway, that's happening today. Any questions about this? Okay. So here's our calendar. Last class we reviewed trig functions. Today we talk about the derivatives of the trig functions. And next class we're going to have another review day. We will talk about inverse functions and logarithmic functions. And two other things are happening next class. First of all, the 4th project is due, so hopefully we're working on it or getting near finishing. And then quiz number 4, which is on 4 classes. So let's just be clear exactly what quiz number 4 is on. It's those 4 sections of material. So quiz 4 is on the chain rule and the stuff that we're doing with trig functions and the derivatives of trig functions today. Okay? Any questions on any of that? Thank you.
Suppose quiz you'll have the different problems will represent different function rules, right? Or most represented to be the most difficult of their kind.
Hopefully I don't write the quizzes so that they're the most difficult. The quizzes are just supposed to be this little check-in. Are you on target right now with where you should be? So I'm hoping I did not pick the most difficult, but certainly you can expect to see several chain rule derivatives and several trig derivatives. Now, technically we did the product and quotient rules before the stuff that's highlighted right now, but the product and quotient rules are fair game for the rest of the semester. So just to be clear, we still need to know the product rule, power rule, quotient rule, all that, okay? So we'll be focusing on the quiz, on the chain rule and the trig derivatives, but we still need to have access to those other ones. Any other questions?
We need the formulas for the product.
I don't think there are any formulas on this coming quiz. So whatever formulas you feel like you want, write them on an index card. All right, so again, we're on page 25, and we'll start up here at the top. I'll go to Garrett for number 1. Tony, are you ready with number 1?
Yes.
Go ahead.
Below is the graph y is the sine of x.
Mhm.
We don't get a way to determine and differentiate this function, but try to sketch the graph of its derivative on the axis.
Okay, so if you have done the reading, then you already know what the derivative of sine is. And in fact, if you paid attention like 2 or 3 classes ago, I told you what the derivative of sine was, just so we could practice with the chain rule. But pretend we don't know any of that stuff, and let's just come back to basics. How do we estimate the graph of a derivative given a picture? We need slopes of tangent lines. So how about we just pick a few points, maybe these points here, draw 5 tangent lines, estimate as best you can the slopes, and it doesn't have to be perfect, and then see if you can plot 5 points that are roughly on the derivative of the graph of this one. Okay, so we draw 5 little tangent lines and we estimate the slopes for this leftmost point. Slope is some positive number. It could be 2, it could be 0.8, it could be 1.3, I don't know, but some positive type thing. So I'll put a point up there. What's the slope of the next one? 0. Okay, that's not an estimate. We know definitively if we pick that top point. So I guess that means that I know, since the top point is right above pi over 2, that's a fact about sine, that definitely the derivative of sine is going to hit the x-axis right there. Okay, how about the slope at pi? Negative something. Well, I just thinking about the symmetry, I believe it's going to be negative whatever we put for the first point, right? Okay, so then I'll put some point down here, you know, like negative 1.2 or something. And then how about the next one? That's definitely a 0, so we hit there. And then the last one, same as first one. So I'm putting a point back up there. And so if we connect the dots, so I'm just going to draw something like that. I don't think that's a particularly good graph that I've drawn because, yeah, the concavity is not reflected here. The graph that I've drawn appears to be ready to just continue on, but we know that the graph is going to repeat. So how about we try drawing something that's a little bit more smooth. And lo and behold, we have something that looks suspiciously like what other function? Cosine. And so here at number 2, in my opinion, this next theorem shows us an amazing connection between the trig functions. The derivative of sine of x is cosine of x. The derivative of sine of x is cosine of x. Now we can debate what the 10 greatest equations are in mathematics, but I just feel like that one needs to be in the conversation. And I know this is something we get very impassioned about, right? This kind of debate, but I think that this is truly amazing, that the derivative of sine is perfectly cosine. It's perfect. Okay, and so maybe, you know, like these 5 points, it looks pretty good, but you know, if you just find, I don't know, we'll pick some random number over here. So how about I come over here to 3, x equals 3, which is just a little bit before pi, right? And I go up here to this curve. This guy has a tangent line. How would you use your calculator to find the slope of that tangent line at x equals 3? What would you do? It is. Let's use the fact that we've just proven, though. Like, how would you use your calculator to actually find the number? What's the slope of the tangent line at x equals 3? Cosine of 3. That's what the theorem says. Derivative of sine is cosine. On your calculator, find the cosine of 3. It is cosine of 3, which is around negative 0.989. Okay, that is the slope of that particular tangent line. It is exactly cosine of that same number. Good. Okay. All right. Next part here, we'll go to Ernie, the proof. Okay, so let's split up this work a little bit. Can we get the 3 tables over here to my right to type in sine of x over x and try to estimate this limit, and then the 3 other tables, can we type in this 1 minus cosine x over x? And we're just looking for numerical information. So we'll type that function into the y equals, and then use the table and see if we can make our best guess. Okay, do we have any guesses? What do we think the first limit is? The groups over here on the right. What is it? 1 vote for 1. Any other groups have a number? On the right, did we get something close to 1? Yeah, okay, so the groups on... Okay. All right, so the calculator is feeling pretty confident that that limit is 1. And then groups here on my left, what is this limit? All right, so just so that both groups can see both things, I typed in both functions here. So my first function is the sine x over x, and my second one is the other one. And inside of my table, I typed in numbers over here very close to 0. And for the sine x over x, I got numbers very close to 1. We see all the 0.999s. I can't type 0 in because then I get sine of 0 over 0. So that's a problem, but sure feels like it's close to 1. And then over here, we get numbers very close to 0. One thing, did anybody over here on the right get something other than these 0.99s? Anybody get something with a 0.17? Yes? Okay. Here is a fact. If I am in degree mode, then all of a sudden, these things change, right? Cosine of degree angles is different than cosine of radian angles. If I go back in my table, I get this. What do we think about the numbers in the right-hand column? What are they close to? What does that e negative 5 mean? Yeah, they're close to 0. That e negative 5 means times 10 to the negative 5. So the right-hand one is still close to 0, no problem. The left-hand one is apparently quite close to that crazy number, 0.1745. And that's not as nice. And so I will tell you, remember on Monday I had said all of calculus is in radian mode. It's actually because of that limit right there. I would really like this limit, sine h over h, to be 1 as opposed to being 0.1745. We'll see why in just a few minutes, okay? All right, so we'll come back to that. Let's accept these two limits as being 1 and 0 in radian mode. All right, let's come down here to number 3 and give us a little bit of practice using the first of these limits. So the first limit is the limit of tan x over x as x goes to 0. Now the first time you see a limit, you just want to plug the value in. So how much is tangent of 0? All right, so tangent of 0 is 0, and on the bottom, also 0. So we get 0 over 0, which means we have work to do. Okay, tangent, we can rewrite. What is tangent equal to as in terms of other trig functions? Sine over cosine. So let's write that. So this is really sine x over cosine x, whole thing divided by x, still with a limit. And that looks like it has several of the pieces of one of my two special limits up above. We see the sine x or the sine h on top and the x or h on the bottom. So what's the only thing that's kind of in my way? It's the cosine. So let's maybe rewrite this. Let's see. So that cosine is in the bottom. So I feel like if I'm going to pull it off to the side, it's a 1 over. And the sine x is up there and the x is down there. Do you buy that those are equal? Times. So do we buy that they're equal? This cosine of x down here. Anytime you have fraction within a fraction, it's just one step to get it so it looks like a normal fraction. That cosine, it's either really on the top or really on the bottom. Which one is it? And if you're not sure, what you do is you say, okay, I can multiply right here by cosine x to cancel that, yes? But if I multiply right there by cosine, I better multiply the bottom of my big fraction by cosine, yes? So is cosine really on the top or really on the bottom? It's really on the bottom. So it's really on the bottom. So x cosine x on the bottom, sine x on the top. So these are equal. And then as I do my limit, what happens to this thing when x goes to 0? That goes to 1. How about cosine of 0? This just might be another problem we've introduced. What is cosine of 0? It's 1. So how much is this? Also 1. That's not a special limit. That's just plug in. So what is the whole limit? 1. So with a little bit of work, we can take a limit we've never seen, this tan x over x, with some fraction stuff, some algebra stuff over there, make it two limits, both of which we can handle. Nikki?
You said that it's x goes to 0 I'm sorry, the first factor would be 1.
Yes.
X is going to 0 with 0.
It would, but half of the room used the calculator to find this limit. So yeah, so 0 in the bottom is no longer just an automatic, it's not going to work. It's now, there's more work. All right, let's try the sine of 2 theta over theta. Sine of 2 theta over theta. Okay, again, it sure looks an awful lot like this first limit, sine of h over h. But the first limit is only good if the thing inside the sine is exactly the same as the thing downstairs. And they're not in this case, right? All right, I have no control over this 2 theta that's inside. You can't get inside of the sine function. But you do have some control over the theta that's downstairs. At least it's accessible to us. If there's a 2 theta inside of the sine function, what would I really like the bottom to be if I'm going to use my new limit here? I'd really like it to be 2 theta. Because if this were a 2 theta, what is the value of that new limit? It's 1. That's what the theorem says. It doesn't have to be x and x. It could be anything and the same thing, right? So if they're both 2 thetas, it goes to 1. But I can't go around and changing the bottom without changing the top. So what do I stick on top in front? Is another 2. So what I did is I multiplied by 2 over 2. And then this part right here goes to, that goes to 1. That's our new limit. So the whole thing goes to 2. The 2 times the 1. So this limit is 2. Okay, let's take a look at the next one. Sine of 3x over sine of 5x. Any guesses? We're going to write it out formally, but anybody have a guess as to what the final answer is? 3/5 seems reasonable. Other guesses? 5/3 also seems reasonable. I'm pretty sure it's going to be one of those two things, right? I mean, like we got a 3 and we got a 5, so somehow we're going to get a 3 and a 5 in the answer. So how do we do it? Let's see. What we're going to do is split this guy up. I'm going to have a sine of 3x. That's definitely upstairs. I'm going to have another fraction, the sine of 5x. That's definitely downstairs. And then I'm going to have a third fraction over here that doesn't have anything yet. So first of all, do we agree it's the same as it was before if all these things are 1s, all those blanks? Is that okay? Like, I mean, it's equal to sine of 3x over sine of 5x if all the blanks are just 1s. Okay, in the first fraction, what would you really like to see downstairs? If we're going to use this limit, you'd really like it to be a 3x, right? The limit says sine of something over the same thing. So I'd really like that to be a 3x to match with the 3x. But if I put a 3x in the bottom, what else do you have to do to balance the scales? Right away a 3x on top. And this is this kind of correcting fraction that we've introduced over here. Can you figure out what goes in the other two blanks? We're going to put a 5x in both. I'll put a 5x in the first one because I'd really like it to match the thing that's inside of sine. And then I'll put a 5x over here because I have to. If I put a 5x upstairs, I better put a 5x downstairs. Okay, and then lots of good things happen. What does this fraction go to when x goes to 0? That goes to 1. This guy's upside down. So it goes to 1 upside down. Is it -1? Yeah, I mean, it's going to the reciprocal. It's flipped over. If the original fraction went to like 7/3 and I flipped it over, it would go to 3/7. So you take 1 and you flip it over and it's still 1. So that guy's equal to 1. This 3x over 5x, well, we better cancel the x's because you can't plug 0 into those things with an x downstairs. And now what does it go to? 3/5. Okay, we were right. The answer was either going to be 3/5 or 5/3. Turns out it's 3/5. Yes, only because it's, well, okay, so flipping 1 doesn't change anything because it's 1 over 1, and if you flip it, it's the same. But if you had this guy upside down, okay, it's a 0. I'll pretend it's divided by 7. You can put anything down there. But if you flip that one, it's undefined. So that one, that limit wouldn't exist if you flipped it over. So it's a good point. That it's something special about the number 1 that allows us to flip it and not care that it's flipped over. All right, so there's 2 questions here we're going to skip over. Maybe we'll come back to number 4, but let's move on to number 5 here. And so now we're finally going to start talking about this derivative of sine of x being cosine of x. Now, you don't need to copy this proof down. I've written it down already just so that we don't spend time watching me write stuff. But here is the proof that the derivative of sine is exactly cosine. The graph that you drew is evidence, right? It's compelling, but it's not a proof. So how do we find a proof? Well, we let f of x equal sine x. And where do we go? We go to the same place we always go when we have a new function that we want the derivative of. Have to go to that difference quotient. F of x plus h minus f of x over h. We've been talking about that since class number 2. And again, every new function we have that we need to find a rule for, we got to go there. It's the only place to go. Okay, so what is f of x plus h in this function? Sine of x plus h. So that's over here, right? Sine of x plus h minus what's f of x? Sine of x. So that's that guy. And then I've got my h in the bottom. Let me take this little detour. I'm interested in somehow doing something with this sine of x plus h. Maybe in your pre-calc class, you saw this formula here in red. The sine of a plus b. It might have been different letters, but I'm seeing some folks nod. So maybe a lot of us have seen this. It's okay if you don't have it just on the tip of your tongue. But it turns out that sine of a plus b is equal to sine a cosine b plus sine b cosine a. And I'm going to use that formula applied to sine of x plus h. So instead of the a in my red formula, what do we have? X. Instead of b, we have h. So in purple down here, sine of x plus h is all that stuff, and you can just check it's that formula. And so then I'm going to come back up here to this big long limit thing, and instead of sine of x plus h, I'm going to put this purple thing, okay? So if you check, you will see that all of that is the purple thing. Used to be sine of x plus h. It's now the purple. Good. Okay, and then there's a minus sine of x, same as it was before. Still divide by h. Okay, and we're almost done. What can you factor out of this term and this term? Sine of x. And if you factor sine of x out of this, what do you have? Cosine of h, that's there. If you factor sine of x out of this, what do you have? 1, but it's a subtract, so it's a minus 1. And then I put the h on the bottom. I put my sine of x out in the front, and I just factored it out. And then the other term is this guy right here. Sine of, did I do something wrong? I did do something wrong. Can't let me get away with this kind of thing. This guy is times cosine of x. So all we did is factor out, and then in this one, I just rewrote that fraction here, pulling apart the sine of h over h and the cosine of x. So do we buy that all the pieces that were there are still there? Okay, and then we have 2 circled things, which should look very familiar to us. The second one we've got more experience with. What is the green thing as h is going to 0? Is 1. That's our favorite limit now, sine of h over h. So this guy is going to 1. Now the 1/2 of the room did cosine h minus 1 over h, right? What did it go to? It went to 0. So then our final answer here is that the derivative of sine of x is, so let's see, we got sine of x times what? Times 0, so that goes away, plus, what's this fraction again? That goes to 1 times cosine. So the whole thing is just cosine. So the derivative of sine is exactly cosine. Which other relationships? Yes. And this limit is actually not trivial if you wanted to like really see a proof. I'd be happy to show anybody after class that's interested in seeing why sine of h over h goes to 1. We just looked at data in a table, and we're buying it, but there is a proof that's readable, it's understandable, but we're not going to go through it today. But you're right, we need that first. Okay, so the derivative of sine is perfectly cosine. So that's good. Remember Actually, we had Lindsay. Lindsay, what did you get for this limit right here? I think there was no zero. It was 0.17. Okay, so if we are in degrees, then this green thing doesn't go to 1. It goes to 0.17. So if we're in degrees, the derivative of sine is not cosine. The derivative of sine is 0.17 cosine. I don't want that. This right here is the one moment where we see why we want radians and never degrees in calculus. Because in degrees, the derivative of sine is 0.1745 times cosine. It's the only reason that you guys are tortured with radians for the next 3-4 semesters. It's that right there. Okay, so if we're buying it, then let's move on to number 6. I'll write down a few derivatives here. So can you guys try with your neighbors, A, B, and C, derivatives of each of those functions? Okay, the first one is okay. First one is straightforward, right? Just derivative of sine is cosine, so that's easy. But for the other two, we have the chain rule lurking around, so we got to be really careful. Okay, for part B, what we want to do is rewrite this thing as some stuff to a power, and we know that the 5th root makes a 1/5 power, and the 7th power is just a 7th power. Now some groups, actually a couple of groups, wrote this as sine of x to the 7th, and then that whole thing is to what power? It's to the 1/5, and it's totally fine to do that. It's the same. But if you do it this way, then you're actually going to have nested chain rules. We have 2 levels of chain rule here. You'll get the right answer. It's going to take a while, and you'll have to simplify it at the end. So it turns out it's better to just go straight at the power, leave it as one number, instead of having a power to a power. And then once I have some stuff to a power, power comes down. 7/5 times what goes here. Sine x, you copy the stuff. Subtract 1 from the power, 2/5, and then times in green. Derivative of the stuff. The stuff is right in there. So what's the derivative of that stuff? Cosine x. So this is our answer. Any questions on that one? Okay, the next one, part C, y prime equals. Okay, this is sine of stuff. Sine of stuff we now know becomes cosine of stuff. So cosine of 5/x. But then in green, we need to multiply by a derivative, the derivative of the stuff inside of sine. So the derivative of 5/x, you're welcome to use the chain rule. Sorry, you're welcome to use the quotient rule. You're also welcome to write it as a 5x to the -1 and use the power rule. For me, I do neither of those. I don't know if you guys remember, but we actually did spend a moment in class talking about the derivative of a constant over x. It turns out it is always, always, always negative the constant over x squared. And that's just a special rule that I have memorized. You don't need to memorize it. But if you do, you save a little bit of time every time you see a constant over x. So this is our answer. Real common mistake to avoid is to say, okay, sine becomes cosine, and then 5/x becomes -5/x squared, putting it inside of the cosine. That is not how the chain rule works. Chain rule says every time you need to copy the stuff once. Every time you do the chain rule, the stuff gets copied one time. So don't do that derivative too early. Okay, number 7 has the graph of cosine of x. We'll want to think about the graph of the derivative. And we'll do this one a little bit quicker than we did before. But if we were to, for example, pick those same 5 points and draw 5 little tangent lines, what kind of a slope does the first tangent line have, the left one? That's a 0. What kind of a number is the next slope? It's a negative, maybe it's a -1. The next slope, 0. Next slope, maybe +1. Last slope, 0. So we plot 5 points. Let's see, it's a 0, then it's a negative, then it's a 0, then it's a, what's next, positive. So we're up here, and then a 0 again. And if we connect those 5 dots, what trig function does it look like? Looks like a negative sign. I mean, it feels like, in a perfect world, okay, the derivative of sine is cosine. We buy that now. The derivative of cosine is sine. That would be super.
So if you take
Yes. Yes. Yeah, it does. So let's first get our one answer that we just kind of established here. Derivative of cosine is negative sine x. So for example, let's see if we can get everybody to talk about the loop that Joe and Garrett are thinking of. Can you guys find the first 4 derivatives of sine x? Find 4 derivatives of sine x. Okay, so we have our 4 derivatives, and this is the loop that I think Garrett and Joe are talking about here, is that the derivatives will just continue to cycle between these same 4 things over and over and over again. So the 5th derivative is the same as which other derivative? 5th is the same as the 1st. 6th is the same as the 2nd. And so we could ask you some crazy question. Does nobody notice the thing on the back of the shirt here? So nothing? We noticed. No comments. Right. Nice. I don't know. No. Okay, so then. So we can ask you some crazy derivative. For example, in honor of the number on the back of my shirt, I can say, what is the 3,141st derivative of sine x? Can you answer that question? I mean, the answer is one of these purple things. So if you just guess, you'll have a 1 in 4 shot. If you guess intelligently, this is an odd number. So then which are the only ones that have a chance? The 1 and the 3. So okay, so now we got a 50-50 shot. If we just guess, it's either cosine x or negative cosine x. Anybody know how? So it's factor. So all right. So I like what Chris is thinking about here. We're thinking about factors, thinking about division. So I guess, so what Chris is saying is that 3,141 is divisible by 3. And he's got a nice little shortcut that he's applying correctly here. Is divisibility by 3 the thing that we're asking in this question? How long is this cycle? It's 4 things long. So the real question is, divide by 4, what do we get? So 3,141 divided by 4 is something. What is it? Okay, so 3,141 divided by 4 is how much? 785.25. This 0.25 is the only thing we care about. That 0.25 means you are what fraction of the way through our cycle here? 1/4 of the way through. So that 1 is your first derivative. It is cosine x. That's it. So we can ask you any crazy question, and really it's just a matter of divide by 4, and that should tell you, if you look at the decimal, where you are in the cycle. Good? Okay. Chris? So Chris's rule is that, how did you know so quickly that 3,141 was divisible by 3? Have we heard this? Have we heard this rule before for 3s? If you add the digits and it's divisible by 3, then the original answer is divisible, or the original number is divisible by 3. It also works for 9. So this number is also divisible by 9. It only works for 3 and 9. Yeah. There are. Yeah, there are crazier rules for divisibility by all the digits, but 3 and 9 are kind of nice ones. 5 is also easy. How do you know if a number is divisible by 5? If it ends in 5 or 0. So some of them are kind of easier, and then there are some that are tougher. 2 is also easy. Okay, number 8 has a lot of data that you guys are going to commit to memory. There are 6 trig functions, which means there are 6 trig derivatives. So the derivative of sine is cosine. We've established that. The derivative of cosine is negative sine. That feels pretty good looking at the graph up above. The derivatives of the other 4 are quite a bit more complex than the 2 that we've looked at so far. Turns out the derivative of tangent is secant squared. That is secant x times secant x. That's the derivative of tangent. That is not intuitive. not in the same way that the two derivatives we looked at are intuitive. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant times tangent, and the derivative of cosecant is negative cosecant times negative cotangent. Okay, you guys are going to memorize these 6 derivatives. Bubba? Which one? Yes. It's negative cosecant times cotangent. Oh, I apologize. It's correct as written here. All right, so you're going to memorize 6 things, but we're going to talk about some of the hints that will make it easier to memorize these 6 things. First of all, what do all 3 of these guys start with? They all start negative. Inside the brackets, what do they all start with? C. All 3 of the co-functions, cosine, cosecant, cotangent, they go in that column and they're all negative, as Chris points out, okay? The other nice thing is that there's a real kind of analog happening if you go from tangent to cotangent. Secant becomes cosecant. This secant becomes cosecant. That tangent becomes cotangent. So really, if you can get in your head those 2, and you understand that the other column is the same, but make it all cos and make it negative, then you've got your answer. The last thing, I said down here, it says memorize these 6 derivatives tonight and then rememorize them the next 5 nights. Okay, it turns out that recently, like in the last 4 weeks, I've learned quite a bit about memory and memory techniques, and I'm proud, I don't know if proud is the right word. Last night I memorized a deck of 52 playing cards, the order in which a shuffled deck of cards is. And I have the deck over here, so you can quiz me on it after class if you want. So I've learned quite a bit about memory, and I will tell you that saying, you know, hey, for me to just say memorize this tonight and then memorize it again the next 5 nights is not fun, and it's also not very effective. So I'm going to give you a mnemonic device that I just made up this morning, and it's ridiculous, and you will improve upon it, but just to give you a sense of how you might do something like this. Okay, suppose that you're interested in getting a tan. All right, maybe you make a trip over to the sea. Do you know the word square? Like it used to be like in the 50s. So you call somebody a square, it means what? You know, they're real kind of straight-laced, kind of like a dork, and I wouldn't know anything about that. I was always in the cool clique, but you know, can you if you want to go to the sea, but you can't because you're a square, and they might not let you out onto the beach with the cool kids. So derivative of tangent is secant squared. Yes? I said it's not good, but it is memorable. And if you create something on your own, it will be more memorable than this ridiculous little story I've got here, okay? So come up with some way to memorize 6 things. Okay, number 10. It turns out that the crazy ones up here, the bottom 4, actually the derivative rules follow pretty easily from the top 2. So can we just pick one and we'll prove one of the bottom 4, and you'll see how easy they are to prove once we believe the top 2. Which one do we want to see? Cotangent. Okay, so you don't need to write this down. We'll just write it real quick. I'm going to prove to you that the derivative of cotangent is negative cosecant squared. How does it work? Here's how it works. You take cotan and you rewrite it as other trig functions. What is cotan really? It is 1 over tangent. What is it also? It's also cosine over sine. And if we already believe the derivatives of sine and cosine, we believe those already, we can use what rule to find the derivative of this? That's a quotient. So we're using the quotient rule. I always start with what downstairs? Sine squared. And in fact, I really like that. If I'm kind of peeking ahead, the answer that I'm expecting here is something with a cosecant squared. What is cosecant? 1 over sine. It's already kind of built. All right, so let's do the top part. So quotient rule says, do we start on the top or the bottom? Bottom. So bottom times the derivative of the top. Derivative of cosine, we believe, is now negative sine. Quotient rule has a plus or a minus? It's a minus. Top times what's the derivative of the bottom? It's cosine. We believe that. Equals. This is really negative sine squared minus cosine squared. That looks an awful lot like one of our Pythagorean identities. Sine squared plus cosine squared is 1. So what do you think is negative sine squared minus cosine squared? Is negative 1. So this is negative 1 over sine squared. Perfect. Because that's really what trig function? Cosecant. So this is really negative cosecant squared. So I can't really help in terms of like an intuitive, oh, I think about the graph of cotan and I should see somehow the derivative is negative cosecant squared. I can't help you there. I am not there myself. But if you believe the easy derivatives, sine and cosine, it's quite simple to figure out what the other derivatives are. It's the quotient rule for all 4 of them. Okay, can you guys try number 11 in your groups? Finding the derivative of x squared times tangent of x. Okay, so as we use the product rule, we just have to write down 4 pieces very carefully. I've got it up there in blue. First times derivative of the second, x squared times secant squared x, plus, and then we continue the product rule. Second is tan x times derivative of the first, 2x. Good? Okay, next page. Oh, just while we're here on this page where I made my mistake, giving Lindsay credit, she was right. That was a 0.01745. I just want to get it on film for you. I messed up. 0.01745. Okay, number 12. So we're finding the derivative of this. What rule? Quotient rule. Oh, goody. So just write out the quotient rule. We're not going to spend very much energy simplifying, but just see if you can get the quotient rule, all the different pieces based on our new derivatives of the trig functions. Again, so I've got my first step from the quotient rule here. I always start with the bottom thing squared. A couple of folks are getting the quotient rule upstairs in the wrong order. And you'll get the wrong answer if you do that because it's a subtraction. So somehow we have to learn the quotient rule set starts with the bottom times derivative of the top, as opposed to the other order, top times derivative of the bottom. So I've got that. It turns out there actually are some nice things that happen when I distribute. So this guy comes in and hits both and gives me a cosine x plus cosine squared. And then there's a plus sine squared x over here. Again, never FOIL on the bottom of the quotient rule. And then what nice thing happens here, that's 1. So this is really equal to cosine x plus 1. And then normally this would be the end of the game, but it just so happens that what can you do here? Yeah, the 1 plus cosine x on the bottom is exactly the same as the 1 plus cosine x on top. So one of those goes away with the entire numerator. So we just get 1 over 1 plus cosine x. Okay, and I wasn't planning on mentioning this, but just as I see this derivative here, 1 over 1 plus cosine x, okay, that's really complicated, but it does give us some information about the graph of this original function. Just pause for one moment and think about if I asked you to graph this original thing, sine of x over 1 plus cosine of x. Oh my, that is very scary to me, right? It's not rational, so we can't apply like all our nice, like even just graphing a rational function is a complicated thing, but now it's like pseudo-rational with trig functions where there should be polynomials. And so how would we even begin? I'm really not sure, but let's take a look at the derivative. 1 over 1 plus cosine x. What is the smallest cosine x ever gets? 0, right? No, it gets smaller than that. It gets to -1. So if cosine of x happens to be as small as it will ever be, then what kind of a number do we get down there? We get 0, which is undefined, which is problematic. What if cosine didn't quite get to -1, but it got to, say, -0.99? Then the bottom is, it's positive, 0.01. Is the bottom ever a negative number? No, right? Because the worst, the smallest the bottom could ever be is 0, which is undefined, but it will never be negative, which means that the derivative here is always a positive number, always positive. What is this original function always doing if the derivative is always positive? It is always increasing. And there's no way I could have looked at sine x over 1 plus cosine x and thought in my mind, oh yeah, that function is always going up. But let's take a look. All right, so we'll pull up GeoGebra here. And we're going to graph f of x equals, what was it? 1, sine x on top. Sine x divided by 1 plus cosine x. Okay, what do you think? Sure looks like an increasing function to me. We've also got vertical asymptotes someplace. Where might those things appear? Where do we go here? Okay, so vertical asymptotes happen when what's true? When the bottom is 0, which is when cosine of x happens to be -1 at that bottom out point. Where is cosine equal to -1? Can you just name an angle? Is it pi, right? And 3 pi and 5 pi. So if you take a look over here at x equals pi, right there is our vertical asymptote, and at negative pi. And if we keep going to the right, I bet you this guy over here is 3 pi. And so you get information about a really crazy function with a derivative. Wasn't too much work. Is this a tangent function? It's a good question because it does look an awful lot like one, doesn't it? Tangent of x. So so it does look like one. Maybe the question is, can we turn, let's see, -5 to 5. I want to go, say, maybe -2 to 2. So maybe the question is, can we turn tangent x into this function by, as Joe says, adjusting the period? Let's try something like that. Okay, so I put a little slider here that's, oh, I didn't do anything in here. Tangent of a times x. So putting a number in the front, that's how we play with the period, right? Okay, so the guy that's going to be moving is going to be tangent of some number times x. All right, and so Joe says, you know, can we make them match up? It looks like they're close at half. Can I, you know, I'm going to be looking and just seeing if I can like maybe pull them apart. Like, are they really equal? I guess is the question that I'm asking. So what I'd like to do is really kind of, you know, like zoom in and just kind of play this game and see if I can't tease them apart. Gosh, they sure seem like they really are. They are looking like they're pretty well stuck together here. So is it the same as a tangent? Yeah, it's a great question, and my first reaction, Joe, when you asked is it tangent, is no, it looks like it, but how, you know, how could it be? And you said, how could it be? But this is just a guess. It's a great question. The only thing I can think to do is maybe try to make it so it's not as bad on the bottom. If I multiply top and bottom by the same thing, we're okay. Downstairs, what do we get? 1 minus cosine squared, right? But 1 minus cosine squared is another trig function. It's sine squared. Upstairs is something worse than it was before, sine x, 1 minus cosine x. And I see that one of these signs cancels, so I don't know if that's any better. 1 minus cosine x over sine x. 1 minus cosine x over sine x. So that's what we've got. The reason that I like this a little bit better is that there's only one term downstairs, which means I can split this up into two fractions. This is really 1 over sine x minus cosine x over sine x. Yes? And then we can start translating. What is that first one? That's a cosecant minus cotan. Okay, so at least it's in more familiar terms. And here's Joe's theorem. We put a 0.5 in there, and it felt like that was the right number to make them match up. So my last thought is to go on Google and just see if we can't find a tangent, because there are half angle formulas, half angle formula tangent. And let's just see, what does it say? Tangent of 1/2 theta is the same as, oh, what's this? That's all right. We can, Joe rediscovered it. Well done. Well done. All right, so there you go. Tangent of 1/2 theta is exactly the same as the original guy. Super. Yeah, and then the 1 minus cosine over sine. I did lots of work for nothing because it turns out I could have just looked at the original, but yeah, good. Joe, well done. Okay. All right, let's take a look. Way more than we can do. Let's take a look at let's do part C right now. That looks pretty tough. So try finding the derivative of part C. Okay, let's see how we're doing. Every time you see square root in calculus, what do? Rewrite it as a 1/2 power. Okay, so we've seen that trick a million times, so we wrote it as a 1/2 power. Again, notice the notation. I know I'm kind of, picky about notation, but again, the bar is raised as you go up the curriculum here. So what do I still have, even as I rewrite it as that 1/2 power? Is this d dx. I haven't done the derivative yet, so that's the little notation that says I still have to do it. And then it disappears because I'm now doing the derivative. Okay, so we know the 1/2 comes down, something goes in the front, negative 1/2 is the power, and then over here in green, derivative of the stuff. What goes in the blue? Yeah, right. So every time we do the chain rule, you copy the stuff one time. If you're not copying the stuff one time, you're making a mistake. In the green is the derivative of the stuff under that radical. X cubed is easy, that's 3x squared. Cosecant x, that's the new one. Again, you'll make up some funny story and you'll remember what's the derivative of cosecant? Negative cosecant cotangent. Now there is a little bit to be desired if you just remember negative cosecant cotangent and you write that, you're going to lose points. What's the problem? There's no x. Cosecant doesn't make sense. I mean, I don't need you to memorize it in your little story, but these trig functions all need to have x after them or something after them. It's not wrong to put more parentheses around those two separate things, but generally, like what you're suggesting would be something akin to this, x cubed plus 5x. If I asked you to find the derivative of this, what would you do? Right, and would you separate them in parentheses? Right, so because of that plus sign, you don't really need to put parentheses there, but it's okay to put them. Okay, so that is that. Let's try 14. I don't know if we'll have time to finish, but let's give it a shot. It says find the x coordinates of all points on this curve, sine x plus cosine x, which honestly I have no idea what it looks like, where the tangent lines are horizontal. Okay, first of all, if you think of a line being horizontal, what attribute of lines do we need to think about? The slopes, right? If I say a line is horizontal, what's true about the slope? Okay, so this we now translate slope equals 0 is somehow really important in this problem. Now we include the phrase tangent, or the word tangent, and what calculus thing do we need to do to find the slope of a tangent line? Take a derivative. So y prime equals derivative of sine x, cosine x, derivative of cosine x, negative sine x. So make sure you're careful with the pluses and minuses. What do I need to make true about this derivative? I need to make it equal 0. That thing right there is the slope of all the tangent lines. I need to figure out when that slope is 0. Okay, so that really means we need cosine x to equal sine x. Okay. Do you have that unit circle picture handy? Can somebody remind us where it is? What's that? That's good. So what page is this on? The unit circle? 20. So if we jump back to page 20, looking for places where the cosine is the same as the sine, that is the x coordinate on the circle is the same as the y coordinate. So you just need to find any points where the x and the y's are exactly the same. So what's one angle where that happens? Is pi over 4. You can see root 2 over 2 for both of them. Is there any other angle where the x and the y are exactly the same? Is it 5 pi over 4? Down in the third quadrant, they're both negative root 2 over 2. So just by thinking about the unit circle, we get our two answers are at pi over 4 and 5 pi over 4. And while you're packing up, because we're out of time, I'm just going to pull up a graph of this guy and just see if we believe that it happens at those 2 points. Okay, so the graph that we're interested in here is f of x is, what was it? Sine x plus cosine x? Plus cosine of x. So we said, all right, well, gosh, that looks like a regular old sine or cosine graph. But I guess what we just figured out is that at pi over 4, the tangent line is flat. Now, pi over 4, if you type into a calculator, is about 0.75. So if you go right around here to 0.75, you are finding one spot where it's flat. And then 5 pi over 4 apparently is somewhere around the number 4, and that's another place where it's flat. And then all the duplicates because it repeats every 2 pi. Okay, you can come 10 minutes early to the next class where we start our quiz if you're interested at 8:30, and we'll see you then.